A straight line wire carrying a current of 3 amperes. Calculate the magnitude of the magnitude of the magnetic field at a point 15 centimeters away 15 centimeters away from the wire Okay, this is the question. So what is the required formula? B is equal to mu naught I divided by 2 pi A. This is the required formula what you have to use. So can we substitute the numbers? So mu naught is 4 pi into 10 to the power of minus 7. That's the mu naught value. I is 3 amps. Whole divided by 2 pi into the distance, it is 15 centimeters. So it is 15 into 10 to the power of minus 2 meter. So this is how you can give the substitutions. So it cancels 2. So the here you can work out 3 5 is 15. So 1/5 of 10 to the power of minus 5 is what you are going to get. So it's 0.5 in 0.2. 1 by 5 is 0.4. Yeah, 0.2. 0.2 into 10 to the power of minus 5 Tesla. So you can write it as 2 into 10 to the power of minus 6 Tesla. So if I'm right, it's 2 into 10 to the power of minus 6 Tesla. So hopefully that's right. I hope. Is there anything mistake I did? Oh, I forgot the factor 2 here. So there's a factor 2 here. I forgot this 2 factor here. It's 4 into 10 to the power of minus 6 Tesla. That is 4 micro Tesla. So that's the answer, 4 micro Tesla. Forgot the factor 2 here. This factor 2 pi cancels out with 2 here. So here 5, 2 by 5 is not 1 by 5 what I get. 2 by 5. So multiply with 2. So this is what you get. You have to multiply with 2 here. So it's 4 into 10 power minus 6 Tesla. Hopefully this is clear. The next part is called solenoid and toroid. This is the thing what we are going to see. Can I clear this, Amma? What happened to others, Lirita and others?
Sir, Lirita went to Tirumala.
Oh. This about puja.
I don't know about puja, sir. I think college had started for her.
Oh, college started for them. Okay.
For us also started, sir.
Okay. What time you are coming actually from college, Amma?
Actually, half day itself, sir, for us. But
Okay.
I think puja is Chaitanya, sir.
Okay.
So they may have up to evening.
Evening 6, huh?
I think so. I don't know correctly, sir.
Okay. So anyway, I will send the record for those who are missing. Okay. Anyway, please ask them to inform me about any changes are required. Okay, so that we can give the changes if needed. Any shift of the classes to morning, so that the morning class what I'm having now I can shift to evening if you are not comfortable with this time. Something like that. We can have a shift. No issues on that. Okay, we can do that and we can discuss. If maximum number of people are not comfortable with this time, I have different slots, so accordingly I can make it. Okay, ma. So we will have a discussion if you have any troubles about this slot especially. So I shifted to 8:30, 7:30. Okay, you can tell me. No issues on that. Okay, can I clear this on?
Yes, sir.
Okay. Now we have to discuss something about solenoid and toroid. Solenoid and toroid. Solenoid and toroid. So we have to see this. So what is a solenoid and toroid? So I'll write the definitions. A, a solenoid is an insulated long wire. Is an insulated long wire. Is an insulated long wire closely wound. Closely wound.
Sir, just a minute, sir.
Ah, yes, ma.
The previous question you have said that 2 by 5 is equals to 0.2, sir, but it's 0.4, sir.
Yeah, I have written 0.4. I told
2
I made a
into
mistake.
0.2 you have wrote, sir.
Yes, ma. 2 into 0.2, I have written it as 0.4. There is a factor of 10 power minus 5 which is multiplying that. So I have written 4 into 10 power minus 6 Tesla. I did that. I have seen that, Amma. I did that.
Okay, sir.
Okay, ma. Anyway, in the video record, you will find it. Don't worry much about that. I did that, Amma. I found my mistake where I have done. I had to multiply with 2. That multiplication I have done. I did that. Okay, we'll see this closely wound. A solenoid is an insulated long wire closely wound in the form of a helix. In the form of a helix. What is a helix? How it looks like? It looks like this. It looks like a spring. When you wind the coil like a spring, that's called a helix. Okay, ma? So how do you achieve that? You take a solid cylinder and wind something like this. Okay, ma? Then what you get is a helix. Then what you get is a helix. This is the structure called helix. Okay, ma? This is what is called a helix. Clear? Clear about this? In the form of a helix. A solenoid is a insulated long wire closely wound in the form of a helix. its length its length is very large as compared to its diameter. As compared to its diameter. Okay, ma? This is what is called a solenoid. The next one is called a toroid. The toroid is a hollow circular ring The toroid is a hollow circular ring on which a large number of a large number of insulated turns insulated turns of a metallic wire, of a metallic wire, of a metallic wire are closely bound, are closely bound. Okay, solenoid, toroid, these are the two equipments used to produce magnetic fields. Magnetic fields. Okay. What are solenoid, toroid? Solenoid and toroid, they are the equipments used to produce magnetic fields. A solenoid is an insulated long wire closely wound in the form of a helix. Helix means whichever looks like a spring. That's called a helix. Its length is very large as compared to the diameter of the wire what we take. If you take the wire diameter is very, very small compared to the length of the solenoid. That's one of the important factors. The toroid is a hollow circular ring. So to draw that, how the toroid looks like is like it's like a circular ring over which we will wind the coil like this. Solenoid is like a straight, this is like a circle. That's what the toroid is. Okay, this is how the toroid looks like. This is how our toroid looks like. Okay, hope you understand what is a toroid and a solenoid. The toroid is a hollow circular ring on which a large number of insulated turns of metallic wire. What is insulated turns of metallic wire? Normally, when you buy the wire outside, you will get along with the insulation, right? That's what the insulated wire is. So you wind that insulated wire around this circular ring. That's what a toroid means. Okay, clear? Hopefully. So once noted, please let me know. Once finished, please let me know, Ma.
Noted, sir.
Now, let me clear this. So, what are the uses of solenoid? Uses of solenoid. Solenoid is used in anywhere you have, like it's used in washing machines. Okay, washing machines. Where we use in washing machines is uh, here we have right now in nowadays we have programmable washing machines. In that, when you press the button, it will let the water in. There, the solenoid will be coming. Okay, and gas pressure lines, gas pressure lines earlier picture tubes, okay, in TVs, okay. So the solenoid is generally for a small magnetic fields, okay, small magnetic fields. It is utilized for small magnetic fields. Whereas when you go for toroid is used for large magnetic fields, okay, large magnetic fields. It's used for large magnetic fields. And so it's also it's actually large magnetic fields like MRI machines. They use this toroids, okay, MRI. And the other devices is like synchrotron. So these are the devices in which we use the toroid and solenoid. So synchrotron is the other one. And these are very symmetric. These have very symmetric geometric shapes. Symmetric geometric shapes. So we use Ampere's law to derive the magnetic field of the solenoid and toroid. So there's not much of information here. So we'll go ahead with the thing, how to derive the magnetic field of a solenoid. Okay, so we derive that now. So there's not much of information, you can find it. So we derive the magnetic field of solenoid. How the magnetic field of the solenoid will be varying. So that's how we have to derive an expression for the magnetic field of the solenoid. A long coil of wire. So a long coil of wire. So how do we take the wire? I'll draw it here. It's like this. So it's like this. When you have this scenario, this is what is our solenoid. Okay. Here, whatever the in-between space, it's like looks like a spring. Whatever the in-between space is there, that is called core of solenoid. As it is, if you don't put anything, it's called air core. Hope you got it. Whatever the space is there between the solenoid rings, that's called a core. Okay. Now, if you don't place anything over there, that's called an air core. Okay. If you put iron bar in between, that's called iron core. If you put copper bar in between, that's the copper core. That is useless anyway. The diamagnetic materials are useless. So we take something like a paramagnetic material or neodymium. If you have neodymium alloy, if you place between the solenoid core, that's called neodymium alloy core. So that's how we call it. So whatever you place in between that rings, helix, that's called a core. So a long coil of wire consisting of closely packed loops. I have drawn for understanding only like this, but it's like all these things should be really winded very, very close. That's most important. Very close loops, okay, is called a solenoid. It's called a solenoid. So this is what the stuff is, okay. The magnetic field, this is the point number one. Point number two, the magnetic field of a solenoid resembles that of a bar magnet. Resembles that of a bar magnet. The magnetic field of a solenoid resembles that of a bar magnet. Note down these 2 points. So once noted, please let me know. Once noted, please let me know, ma. I'll wait. No problem.
Noted, sir.
Okay, ma. Right. So I'll clear this. The third point. Inside the solenoid. Inside the solenoid. Inside the solenoid. The magnetic field. The magnetic field is uniform and parallel to the axis of solenoid. So you take this solenoid, this is called the axis of the solenoid. This is called axis. Okay, ma? This is called the axis of the solenoid. And the magnetic field, whatever it produces, it is parallel to the axis of the solenoid. And one more important point is that we assume, this is an assumption actually, we assume that the magnetic field outside the solenoid is 0. In fact, it's an assumption, but not actually, but it's a field will be less amount of field. Actually speaking, it's less amount of magnetic field. That is what it will be. It will be less amount of magnetic field. We cannot assume that it's a 0. We cannot assume, but we assume still for the simplicity, we assume the field outside the solenoid is 0. There won't be any leakage of magnetic field. That means that It's like a perfect solenoid. A perfect solenoid. This is what you have to know. A perfect solenoid will not have will not have any kind of magnetic field leakage outside. Magnetic field leak outside. So that's it. These are the things you have to know about solenoid. Then we'll derive the condition.
Noted, sir.
Okay. Now let's see this next part. And now consider that I said that's an air core solenoid. You consider first an air core. Air core means air is in the middle, nothing is kept. And assume that I is the current. Current I is flowing through the solenoid, and they are about n turns, and the n is the n turns. N is the number of turns, and L is length of solenoid. Length of solenoid. We define a factor called small n, which is n by L, which is called number of turns per unit length. We define a factor. N is the number of turns per unit length. Okay. And we say that B is magnetic field inside solenoid. Magnetic field inside solenoid. Magnetic field inside the solenoid. So that's what the magnetic field is. Okay. Now, what we had to do is we had to apply the Ampere circuital law. So how to do that? That we'll see. So we consider that this is like a cylinder, but actually this is air. And over this cylinder, when I put a cross like this, it means that the wire is going inside. Okay. Wire is going inside. There is a portion wire is going inside. And if I circle and put a dot, the wire is coming outside. So it's like this. It is wounded like this. Okay. Hope you understood. This is what it is. Okay. So wires are winded like this. Okay. We assume this situation. Now we consider a rectangular Amperian loop here. Consider a rectangular Amperian loop. Amperian loop need not be circular all the time. We can consider Amperian loop is like a rectangle also. Amperian loop. So we consider a rectangular Amperian loop. So just a minute. We consider rectangular Amperian loop. It is our PQRS. PQRS. That is our rectangular Amperian loop. So we have to find the magnetic field all along. So we apply the Ampere's law. Ampere's law is integral d bar dot dl bar is equal to mu naught times I. This is what you have to remember. This is called Ampere's law. So this is the funda what we are going to apply all along. Okay. So please note it.
Noted.
Okay, right. Now, let's clear this. Now we have to apply this circuit law very, very carefully. Now you have this Amperian loop, PQRS. And now you see this magnetic field will be inside the loop. It will be there along the axis, and outside the loop, it is 0. This you have to keep in mind. So that is the ideal condition. So I want to find the integral d bar dot dl bar, that is equal to mu naught into mu naught times current closed enclosed by current enclosed by PQRS. Okay, we'll see. I'll tell you how to handle this. Okay. Now this is about the PQRS. Now, if I have to evaluate this, what I have to do is B bar dot DL bar. This is total. Total BA bar dot DL bar is nothing but the B bar dot DL bar along PQ, that is from P to Q, plus integral B bar dot DL bar along Q to R, and integral B bar dot DL bar, sorry, B bar dot DL bar, that is from R to S, plus integral S to R, S to P, sorry, S to P, B bar dot DL bar. Okay, please note it up to here. After that, three easy things we can remove. First, total B bar dot DL bar will find. Three easy things we can remove. I'll tell you how. You see, the magnetic field, assume that this is the direction of the magnetic field. Okay. And now what is this angle? For RS, it makes 90 degrees. And SR also makes, SP also makes 90 degrees. And SR is outside. So let us see what happens with QR. So QR is, let me evaluate this one. That is QR. Let us say this length is, doesn't matter, whatever is the length. So it is mod B bar, mod DL bar. What is the angle? 90 degrees. So cos 90, right? Plus the next one. SR is outside. So this portion, there won't be any magnetic field. So this portion is 0. Now, SP, you see SP, that is also 90 degrees. So again, mod B bar, the SP condition, mod B bar, mod DL bar, again cos 90. So this portion is also 0, cos 90 is 0. So this portion is also 0. You have only one surviving term, that is P to Q B bar dot DL bar. Simply it has come up to this extent. And now what it can be? It is nothing but the length of the solenoid. So you get, this is simply is equal to B times L. If B is constant, that is, we assume that the magnetic field inside the solenoid, that is also constant. It produces magnetic field, constant magnetic field. Of course, that is B times L simply. Why? You can see that it is mod B bar, mod DL bar. What is the angle between them? 0 degrees. So cos 0. So this is the only surviving term you have. So that is B times L, where L is the length of the solenoid. Up to here, please note. Now, what is B actually? B is total magnetic field. Total magnetic. Okay. Remember this. This is very important. B is total magnetic field of the solenoid. Once finished, please let me know.
Noted, sir.
Okay, good. Now there is one logic. So BL is equal to, you see this one. I said the solenoid is having n turns, okay? Now, tell me if I current flows, I is the current, which is flowing through one turn, okay? It produces a small field, let us say B1, okay? Now, the same current flows through the second turn, that is B2. Same current is flowing through the third turn, that produces B3. But the number of turns, the radius, okay, all are same, they are closely winded. These magnetic fields will add up. Okay, now the total magnetic field is contributed by all the turns. Okay, are you getting the logic? Yes or no? Please let me know. See, we have seen the magnetic field produced by one ring. Okay, this also we have seen. See, if the number of rings are increasing, the magnetic field has increased by n times. This we have seen that. I shown that expression also. Similar case here, all the n turns will contribute to the magnetic